Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 18, Mars. I'm Gary Jordan, and I'll be your host today. So this is the podcast where we bring in the experts, NASA scientists, engineers, astronauts, bring them right here on the show and talk about all the coolest parts about space. So today we're talking about Mars with Doug Archer, which I feel like is a good topic to bring up now because next week NASA is launching a brand new podcast called Gravity Assist. Hosted by Dr. Jim Green, NASA's Director of Planetary Science, the show will focus on planets and the solar system and beyond. So if you love planetary science, definitely subscribe to that show. It's going to start with a 10-part series on our solar system that starts with the sun and goes all the way out to Pluto and beyond. I know I'm pretty excited about it. So as sort of a taste of what you're going to get on Gravity Assist, Doug Archer will talk about the fourth planet from the sun today on Houston We Have a Podcast. Doug is a planetary scientist at the NASA Johnson Space Center here in Houston, Texas. And we had a great discussion about the red planet, what it's made of, what it's like on the surface, and why it's such an intriguing place for humans to visit in the next giant leap. So with no further delay, let's go light speed and jump right ahead to our talk with Dr. Doug Archer. Enjoy.
T-minus 5 seconds and counting. Mark. Launch commit lights are correct. There she goes.
Houston, we have a podcast.
Yes. So you're a planetary scientist. That's your title, right? Planetary scientist.
Yep.
So I'm guessing it's exactly what it sounds like. You know the science behind why a planet is the way it is, why it's a planet and how it works and all that kind of stuff. And your specialty is Mars.
Yep. Yeah,
Sweet.
I've been working on Mars for about 13, 14 years now.
Wow. So what was it that originally fascinated you with Mars?
So like lots of kids, when I grew up, I was interested in space or being a pilot or something like that, or an astronaut. But then when I was, I think, 16, I read a book called The Case for Mars, The Plan to Settle the Red Planet and Why We Must. And it was written by a guy named Bob Zubrin, and he laid out this whole architecture for how we would get to Mars, the rockets that we would, or the type of rocket that we would need, what the habitats would look like, how long it would take to get there, just this whole architecture of how we would get to Mars, and then ultimately, like the long-term goal, right, is turning Mars into a more Earth-like place. But that's like the super long-term goal.
Right.
So this book came out, again, I think in 1996 or something like that, and there was this big cover article in Newsweek and other magazines. It kind of made big news, and I just read the articles, read the book, and just got fascinated with the idea of human exploration of Mars, and then learned more about the planet Mars. And when I was an undergrad, I was trying to figure out what major I wanted to do, and what I wanted to major in, and I was thinking about, well, I think I'm kind of good at this, and I'm kind of good at this, but what I was really passionate about was Mars and Mars exploration, and I didn't know how to make a career of that, because where I went to undergrad at Brigham Young University in Utah, we didn't have any kind of space-related program there. So I just majored in physics. I found a professor who was similarly interested in Mars, and another professor in the geology department who had actually done...
At Brigham Young?
Yeah, at
Okay.
BYU. There just happened to be a few other kind of space enthusiasts there, or
Cool.
Mars enthusiasts. So they kind of pointed me on the road. And so I took an Introduction to Planetary Geology course as an undergrad and just loved that. And they pointed me on the course of, all right, here's some courses to take to prepare for grad school, and this is where you should apply. And one of the places that I applied was the University of Arizona, which has one of the few programs in planetary science in the country, or one of the few PhD programs. And I got accepted and started there in August of 2004. And the reason that I went there is because they had just won the contract from NASA to do the 2007 Mars Phoenix Scout mission. So I got to see, so I went in, and my advisor was the principal investigator for that mission, so kind of the boss over the whole mission. So I went in as a first-year grad student and worked on the Phoenix project right after it had been selected. And so my career as a grad student spanned the right after selection, all of the design work, verification, all of that for Phoenix, and then landing, surface operations, and then doing the science on the stuff that we learned on the surface. And the mission ended in late 2008. So I just had this walked into this great opportunity of getting involved in an actual Mars mission as a graduate student, and just loved working on Mars, loved the mission operations aspect of it. I mean, one of the most exciting times in my life has been the 2 times when I've been able to remotely witness a robot landing on Mars, and just the absolute thrill that is, the 10 to 15 minutes of, okay, this is it. This is gonna, everything comes down to this moment, and then the thrill of seeing the first pictures from these landing sites that no one has ever seen before. Like, it is just an absolutely amazing experience to see these pictures coming in for the first time from another planet, and just having that feeling of discovery and exploration.
I can imagine, because I mean, you have such a passion for it since you pursued it so far, getting a PhD in planetary science, being fascinated with planets, and then being able to work on learn from a robot that was actually on the surface of another planet.
Yeah.
That is crazy. That is awesome. So that makes me think, why... So, your specialty is Mars, and that is a huge part of NASA's journey to Mars, right? We really want to put boots on that planet.
Yeah.
But why that planet? Obviously we have Venus, we have Titan's looks pretty cool, Enceladus. Why? What is it about Mars that's so intriguing?
So as far as the boots, it all kind of comes back down to the boots on the ground aspect that you're talking about. Like, Titan and Enceladus are very interesting places. Europa, there's other really cool places in the solar system, including if you're looking for life outside of Earth. There's other places that you can go look. Mars is the planet that is the most likely to host life where humans can actually go. Like, we are years, and I mean probably decades to centuries away from being able to safely go to Enceladus or Titan or Europa or whatever with people.
That's pretty far away.
Yeah, we have the technology to get us to Mars, and I think that we know that in the Martian past, Mars was a lot more Earth-like than it is today. We don't exactly know how that happened. It's still an open question as how could Mars have sustained this warmer climate, for various reasons that we could get into.
Yeah.
So we don't exactly know why that's the case, but we know from geologic evidence that Mars was warmer and wetter in the past than it is today. And we know from Earth that pretty much as soon as life could have existed on Earth, it did. So we don't know how life originates exactly, but again, from Earth, we say, hey, just as soon as the conditions were right for life to exist, we find evidence of life. We know that those same conditions existed on Mars. So the question is, can we go to a place where we can find evidence of past, more likely past, but potential present life on Mars? And then as far as the astronauts will allow you to do a lot more science than robots will.
Right, because so we talked about this in a previous episode with Bill Foster about space communication and how difficult that's going to be. If you get a signal to Mars, it's going to take 8 minutes up to 40 minutes round trip to do anything. But if a human was there, they can make decisions rapid fire.
Yeah.
You can get a lot more done in a shorter amount of time. I'm guessing that's like pretty much the basis of why humans are that much better. Probably also the observational aspect of it. They can
absolutely
find cool parts.
Both of those things together.
Yeah.
So I'll give you an anecdote to show you kind of the limitations of robotic exploration. And first I'll talk up the benefits of robotic exploration. First of all, it's something that we can do today, right? We've been doing it on Mars now for over 40 years, where the Viking landers landed in late 1976. So we have a lot of experience at operating robots on the surface of Mars, and they are very capable. Like, the rovers can hold a lot more stuff than astronauts can. They don't have to continually go back to the hab. You don't have to send food. You don't have to worry about oxygen.
Right.
So it's a lot simpler. However, robots are only as smart as the humans that program them.
Right.
And because we have no capability of repairing or fixing something if it goes wrong. We're very cautious about how we operate the rovers or robots. And as you said, we have this communication issue built in that makes it so that, a lot of people think that when we're operating the rovers on Mars, it's a man or a woman sitting in a room somewhere with a joystick in front of a TV, kind of, driving the rover.
Right.
But at its closest, Mars and Earth are, there's a 4-minute one-way light time delay between Mars and Earth.
Right.
So 8 minutes round trip. And at their farthest away, it's about 20 minutes one way or 40 minutes round trip. Mm-hmm. So you can imagine, anything that you're seeing is delayed by 40 minutes. So there's no way, in the worst case, 8 minutes, best case, there's no way that you can do any kind of real-time operations under those circumstances. So what we do is we plan a whole day at a time. So during the Martian night when the rover is asleep, we're awake planning the next day. And when the rover wakes up, the first thing it does is kind of check in with Earth and get the instructions for what it should be doing that day. Mm-hmm. And then it will go through the whole day of planned operations and then go to sleep, and the process repeats, wakes up. And so it sends back the data of what it did that day. We look at the data of what it did, how things went, and then plan the next day. So because of our conservatism, because we don't want to break anything, and because the robots are only as smart as we make them, mm-hmm. you'll have funny instances where, for example, the Phoenix lander, which we knew had a very limited lifetime because it was in the northern polar region, so at some point the sun was going to set and not rise again for 6 months. So, there's nothing that we could have done to make that mission last for years. We knew that going in.
Because how cold does it get when the sun sets?
When the sun sets kind of for months at a time, it can get down, I think, to like minus 130, which is the frost point for carbon dioxide. So the Martian
Fahrenheit?
atmosphere, Celsius, sorry. But at that
130
point,
Celsius.
they're relatively similar. So the Martian atmosphere is 95% carbon dioxide, and it gets so cold that the atmosphere starts condensing out onto the surface as dry ice. So our lander, after at the end of the Martian winter, northern winter, was buried under a meter of carbon dioxide ice.
Okay, so no coming back from that.
Yeah, so we took pictures with a high-resolution camera around Mars, and it looks like one of the solar panels, which is kind of the size of a kitchen table on the lander. It had 2 panels about that size, and then the lander itself was about the same size. Mm-hmm. And it looks like one of the solar panels was broken by that. So we knew that there was almost no chance that we were going to survive to the next year. We knew that going in.
But the polar ice caps are they're super interesting. That's why you sent it there, right?
So we were just south of the permanent ice caps, but so there's the seasonal cap of CO2 and then water ice as well.
Cool.
But then the reason why we chose the location to send Phoenix is that underneath, or we saw from orbit the signature of water underneath soil, and we went to confirm that, and we did. We in a few ways. One was just during the landing process, our thrusters that we used to land safely blew off the covering of the soil or loose dirt right underneath the thrusters, and you can see this ice cemented ground. Then we had a robotic arm to dig down and found that depending on exactly where we dug, between 4 and 15 centimeters deep, we found this ice layer where in a couple places it looked like it was almost pure water ice, and most of the area that we uncovered was ice cemented soil. So you could imagine taking a dish full of dirt, adding water to it, and throwing it in the freezer. And at these temperatures, or at the Martian temperatures that I was talking about earlier, it's as hard as concrete.
Wow.
But just
really hard to dig then, probably.
Yeah, so we couldn't dig into that. The best we could do, we could kind of scrape along the surface and collect what we scraped, but we also had a drill that could drill about a centimeter into the ice, and then we'd collect the tailings that came from the drill.
Okay.
But to get back to the human exploration point, one day on Mars, we're digging with the Phoenix lander, and so what you do, right, you say, okay, dig here and then dump here. So dig, in this area that we define, and then dump off in some other area.
On the surface, right?
All on the surface.
Okay.
So the arm is digging, and it goes to dump, And it just so happened to choose a path between the dig location and the dump location that there was a rock in between it that wasn't a big rock. I mean, it was, maybe 8 to 10 centimeters across, not a huge rock. But so on like the very first scoop, and it was supposed to scoop for a while, on the very first scoop, it grabs a scoop of dirt, hits the rock, and just stops. Because it doesn't know what to do, right? And then we didn't program it to say like, oh, okay, well, if you hit a rock, then try this other path and
right. The only thing it knew was you go from here and you go to here. It wasn't expecting an interruption. Yeah. So that's the kind of thing. So and then you go in the next day, and you see that wow, things didn't go as planned. We only have this one tiny little scoop. There was supposed to be a whole trench there. What happened? And you go look at your telemetry and say, oh, we hit a rock. And it wasn't even a very big rock. And that's the kind of thing where, for a human, right? Like, oh, I hit a rock. I'll slightly move my hand and go around the rock. Right. And you don't waste an entire day from hitting a small rock. And we encounter stuff like that all the time because, again, the robot's only as smart as we are. If we encounter something unexpected, the conservative approach is usually to say, okay, just stop, and we'll tell you what to do tomorrow. So, a human doesn't have those kind of limitations. As you're saying, we have the observational ability to, first of all, analyze the landscape and say, those look like the most interesting places to go investigate. Let's go there. And then you can go do things very quickly. So the pace of exploration with humans can be a lot faster. Now, the cost is also a lot higher. Sure. So
you've got to figure out kind of what's your science return per dollar. But the pace of explorations with humans can be much, much faster.
Right.
So as another example, the Curiosity rover or the Mars Science Laboratory, which has been on Mars now for almost 5 years.
Wow, that's right.
We have driven just over 16 kilometers, which is a long ways. But for a human in a human-class rover, that would probably be a good day or two of driving.
Right.
Now, we've done a whole lot of science along the way, so you can't, it's not just, we landed and we've been doing nothing but driving.
Hit the gas pedal and just go for
5 years.
Yeah.
But just to give kind of a sense of scale, like I think the Opportunity rover relatively recently surpassed how far the Apollo astronauts had driven on the moon.
Wow.
And I think so it took Opportunity over 10 years what the Apollo astronauts did in like 3 days.
Right.
So you can see that there's this difference in scale of kind of what you can accomplish. And it's interesting that you'll find that a lot of people who have experience with robotic exploration actually operating the rovers, many of us are big proponents of human exploration because we understand the limitations, because we know just how much more we could learn and how much more we could do with humans there.
Yeah. So so as a planetary scientist, I guess we should have addressed this a while ago, but you do you pick the locations where the rovers are going to go, and which rovers are you kind of working with now? Are you working with Curiosity?
Yeah, so right now I'm working with Curiosity. The only other rover that's currently operational is the Opportunity rover,
right?
Which is amazing. It's been going for more than 13 years now.
Yeah. Way past its expected.
Yeah, the prime mission was supposed to be 90 days. So, they're like 4,000% of lifetime or something. I forget the number. But yeah,
awesome.
Much longer than they ever expected, which is just great and a testament to the engineers that built the rover. So I work on Curiosity, and the way that the landing site selection process works is it's a fairly democratic process. They'll have multiple meetings for years in advance of launch for scientists to come, and you can propose to land wherever you want. You can say, well, okay, within reason. So the engineers will say, okay, for this lander it needs to be, within 30 degrees of the equator or 45 degrees of the equator or whatever, and you have to be able to fit a landing ellipse that's this size, and so the landing ellipse is the area in which you are confident your lander is going to land. So you'll say for the MER rovers, the landing ellipse was like 100 kilometers long and I don't remember, 15 kilometers wide or something like that. So you'd have to say, all right, you have to find a place where we can safely land anywhere inside of a 100-kilometer wide or long ellipse by 20 kilometers wide. And MSL, because we got better at guidance and during entry, the landing ellipse was only like 12 kilometers long, I think, and a few kilometers wide. So a factor of 10 improvement over what we'd done before, which opened up a whole host of other landing sites.
Because now you don't have to worry about things being in the way.
You don't have to
100-kilometer kind of.
Yeah, you can
ellipse.
pick a lot more interesting places because your safety requirements are relaxed from just kind of the physical geography standpoint.
Mm-hmm.
But so given those restrictions, you can propose anywhere you want.
Mm-hmm.
And you go and you advocate, you make a presentation, and you advocate for this particular site and why your site is better than any of the other ones, the questions that we're going to address by landing there, why this site best meets NASA's goals and the goals of the planetary science community. And so, I mean, I think they start out with a list of like 30 to 50 landing sites or something like that. And over time, it'll get narrowed down to usually around 3 or 4. And then what happens is there will kind of be like a community consensus around, this is our top pick. Mm-hmm. So that's kind of the democratic side of things. Mm-hmm. But then ultimately the decision is made, I'm not exactly sure who, but program officer level, NASA headquarters level, where they'll say, because sometimes the scientists will pick things that are like, this is really interesting, but it's a little bit riskier than some other site. And, for the scientists, we say, yeah, we want to do it. And NASA headquarters might come in and say, guys, it's a lot more important for us to land safely than to answer this particular question.
Right.
So we're going to choose this site. But for the most part, it's very democratic about, basically anybody with a good idea can submit a candidate landing site, and then it gets talked about in the community for years. You analyze it for safety. We actually use our orbital assets that are around Mars now to take a lot of pictures of it to make sure for safety reasons that it's safe. Like another little anecdote with Phoenix, we had 4 candidate landing sites, and the top, I'm almost positive if I'm remembering correctly, the top we had decided on one landing site of, hey, we think this one's going to be the best, and then we had the high-rise camera get to Mars kind of right at the tail end of this process, so we didn't have the high enough resolution, or we didn't have as high a resolution pictures as we do today. Mm-hmm. So HiRISE, one of its top priorities was evaluating these potential Phoenix landing sites, and this one that we had decided was going to be our top site, the principal investigator of the HiRISE instrument, which is also built at the University of Arizona, where the Phoenix lander was. So the PI of HiRISE was a good friend with the principal investigator of Phoenix, and he sent him an email with the picture of this landing site, and it was filled with massive boulders that were just below the limit of resolution of this other camera, and it would have been an awful place to land. So at that point, okay, all the other arguments are thrown out because it's not safe.
Oh yeah.
And so we went to, I think, Plan B, and they imaged that one, and it was like, yeah, that one looks good.
Wow. Okay, that would have been pretty bad.
And I think, as I recall, we got the image around Halloween. So he sent it with the caption of like "Happy Halloween," and the whole thing was like, shaded red or orange or something to make it look even scarier than it actually was. So
wow.
Yeah, at that point we knew, okay, we're not going to land there. Let's go somewhere else.
Wow. So I mean, there's rovers all over the place, right? You said we've been landing on Mars since the late 70s, since 76, I think you said was the Viking,
yeah.
Right? So there's a lot of interesting things about Mars. So, I mean, main question, right? So if you're looking at Mars and you want to know, okay, what is this planet? Why is this so interesting? Uh-huh. Main question, why is it that red or burnt orangey color? Like, what is the official color of Mars?
Right. Well, red, I mean, that's
red?
One of Mars's nicknames is the red planet.
Right,
I mean,
okay.
That's when I'm writing stuff about Mars, I will frequently call it the red planet just to avoid repeating Mars or Martian over and over.
Yes.
So Mars gets its red color really from, essentially rust. So you have, and some parts though, or many places on Mars, it's interesting that it's really only skin deep, that you can uncover or if we go and either brush off or just blow away some of the dust, you get to underneath it, it looks a lot darker. But we have this bright dust deposits kind of all over on Mars, because Mars can have these global dust storms. So you get this stuff distributed everywhere.
Wow.
And the red color really comes from the oxidized iron, which, again, rust or hematite, the specific mineral, or other things like that give Mars its red color. So you had oxygen in the atmosphere, which is reacting with minerals on the surface to produce this iron oxide, which gives Mars its red color.
Huh. Is it sharp, the dirt, or what do you call it, dirt, or do you call it regolith?
Soil, or we're moving towards calling it soil on Mars, even though some terrestrial people say soils have to have living things in it, but we like regolith on the what we're calling soil on Mars is different from regolith on
airless
the moon
bodies.
or other airless bodies.
Yeah. Okay. Nice. But there's oxygen in the atmosphere, not a lot though, right? Like you can't step out on Mars, if you were to land on Mars and step out of your capsule and breathe the fresh air, right? There's not a lot.
Correct. So Mars' atmosphere is 95% carbon dioxide, 2% nitrogen, and 2% argon so that only adds up to 99%. So then there's other little bits, and oxygen is one of the other little bits, but it's much, much less than 1% oxygen.
But it's enough to rust make the
and that's the idea of that's where at some point in the past Mars' atmosphere probably had more oxygen,
right,
and that oxygen reacted with what's on the surface.
Okay, so compared to Earth, our Earth is mostly like nitrogen, right? 70% nitrogen, and then
80%, roughly 80% nitrogen, 20% oxygen is kind of the.
Okay, so only 20%. That's awesome.
But so the other thing though is you can't. Not enough oxygen to breathe, but it's also less than 1% of the atmospheric pressure of the Earth. So really low pressure, no oxygen. There's a lot of different ways that you could meet a quick end on Mars if you just decided to step outside without any kind of protection.
Which goes to our earlier point, as if you were to go there, you would probably need a habitat, and you would need rovers, and you need all kinds of spacesuits to walk around. You need all kinds of things to survive on Mars. But I mean, Mars is not just it's not just a blanket of the soil, of this red soil. It's got hills and mountains. It's got one of the biggest,
the biggest volcano in the
solar system, right? So I mean, there was a past of geological activity, right?
Yes, absolutely. So when we look at the history of Mars, we see a lot of evidence early on, like I was saying earlier, that Mars was warmer and wetter than it is today. Now, it's still an open debate about how warm it is and how wet it was, but we know that it's warmer and wetter because we see evidence for rivers and lakes. So there was likely, at the very least, snow, possibly rain. And these aren't like little streams, large channels, huge lakes. It's possible that there was a massive ocean. So we know that Mars was warmer and wetter in the past, and then kind of after that, Mars dries out, and then you have all this abundant evidence of what you're talking about, the volcanic activity, really, all over the place on the surface of the planet. That has really kind of resurfaced a lot of Mars. We still see a lot of craters, but there's volcanic activity all over the place. And like you said, so we have Olympus Mons that's like 20 kilometers high, the biggest volcano in the solar system.
Super big.
So MSL, or the Curiosity rover, landed at the bottom of Gale Crater, which is a 150 kilometer wide crater that's 5 kilometers deep, and right in the middle of the crater is a 5 kilometer high mountain. So it is a mountain. It's not a hill.
Yeah.
It is huge. This is, it's like rivals Mount Rainier or Mount Shasta or something. Like, it is big.
Yeah.
It's really big. It would be one of the largest mountains in kind of the lower 48 United States.
Wow.
And we're still kind of trying to figure out exactly how it was formed. One of the interesting things about it is that it was not formed by, so most mountains on the Earth are formed through plate tectonics, right? The continental plates kind of crashing against each other, or a subduction of an oceanic plate pushing up mountains, and that's how we get mountains on the Earth. On Mars, we don't really have plate tectonics, so you can form mountains either from volcanoes. There might be some tectonic activity, but what we're seeing in Mount Sharp is likely the result of actually the crater to some degree filling up with sediment, so dirt, rock, whatever, around a pre-existing central peak in the crater that we still see some evidence for, but what the mountain that we see is much, much larger than the central peak would have been, and then eroding away into the shape that we see today. So completely different form of, or completely different formation mechanism for a mountain. I can't think of any example or any place on the earth where you would ever see anything like this.
Wow.
But still, we formed this 5-kilometer high mountain, and the cool thing about it, though, is because it is this composed of sedimentary layers that were laid down over hundreds of millions of years, as we drive up the mountain, we're seeing different layers, and we get a window into Mars's geologic past. So we can learn something about what was Mars's environment like 3.5 billion years ago. And the reason that we picked this location is that the lower part of the mountain was created when Mars was warmer and wetter, and the upper part was created when Mars was colder and drier. So we're going to have the opportunity to drive across these materials that span, again, hundreds of millions of years of geologic time, where Mars went under this, where Mars underwent this fundamental geologic change or climate change. So trying to figure out, what happened.
It's kind of like, so I mean, I'm from Pennsylvania, so I remember driving down the highway and seeing, they blew up some of the rocks, and then you can see the layers.
Oh yeah,
of the
road
rocks.
cuts are the geologist's best friend.
Yeah, so it's kind of like, I mean, the mountain itself, are those, layers of rock as you drive up. I guess that would be kind of a good comparison. Yeah,
it's just on Mars, it might actually be a little bit easier to interpret some of it, because on the Earth, again, the mountain, you had the layers, kind of laid down, creating the rock, and then you'll have these other tectonic events that push them up. And in the process, things get all kinds of jumbled. But on Mars, there was no tectonism. So they the rocks got laid down, and then they get eroded away, but there's nothing that, it was pushed up from kilometers deeper or overturned, creating all kinds of confusion. So if we can get there to the right places, unfortunately on Mars there's no road cuts, so we have to do with we have to use what we're given. But it's very similar to what you'd see in a lot of places on the Earth.
Wow. Okay, so another main difference, right, is I guess the atmosphere. We just had a recent discovery about how Mars's atmosphere has changed over time, right? And how what's the radiation environment like on the surface?
So, the atmosphere, so that's two things. The atmosphere, again, we know that it was warmer and wetter in the past, so that we know that the atmosphere had to be a lot thicker than it is today to hold in that heat. And we're still unclear how Mars was able to be as warm and wet as it was. There's some kind of magic combination of pressure and chemical elements in the atmosphere that had to have existed to allow Mars to be warmer and wetter, and that's still something that people are debating today. So how that relates to radiation is that on the Earth, there's a few things that protect us from the radiation environment in space. One is Earth has a magnetic field. That does a lot of the work. The other thing is we have a relatively thick atmosphere, so anything that makes it through the magnetic field is generally going to get stopped in the atmosphere. So Mars doesn't have either of those things. And there's other types of radiation as well, so like ultraviolet radiation, which is not great for people. Earth has an ozone layer. Mars, depending on the season, will have a tiny bit of ozone in the atmosphere, but not really enough to effectively shield you from UV. So you get ultraviolet light down to the surface of Mars, which on the Earth would be sterilizing. Like if you stick that's one of the things that we do on Earth to sterilize water or whatever. If you shine it with UV light that Mars is getting bathed in all the time. So the very surface of Mars is not terribly hospitable to life. But the good news is, the iron oxides, for example, are a very good sunscreen. So if you're under a couple of microns, so like a human hair's width of iron oxide, will do a pretty good job protecting you from ultraviolet light. So that's one type of radiation. The other type is, again, the kind of the space radiation environment where you have these high energy galactic cosmic rays and stuff the sun's shooting at you all the time.
Oh yeah.
So this is something that you have to be for robots. It's something that we have to be aware of as well, because we actually have to use special electronics that are like radiation hardened. For people, you have a couple things you need to do. One is you have to have some kind of shielding, and then the other is just kind of what your mission architecture is. You want to spend as little time in space as possible.
Right.
But I mean, what I think, there's a few things that you can do to shield you from radiation. Like recently, we have a radiation detector on Curiosity on Mars. Relatively recently, we were right up next to a hill doing some science, and the counts on the radiation detector went way down, because this radiation, it's not just coming from the sun, it's coming from everywhere in the sky, basically uniformly. So if you can block out any part of the sky, you're going to lower your radiation dosage. So if you're an astronaut, you'd probably want to build your habitat up close to a little hill or a mountain, and maybe one of the first things that you do when you get there, or you had robots do this before you got there, is start filling up sandbags and put it on the roof of your habitat, because you just need more mass. That's what the atmosphere is on Earth. It's just more mass in between the radiation environment and the ground. So you just need more mass on top of you to shield you from this radiation. And then again, like the UV stuff, an astronaut in a spacesuit will be just fine.
I'm imagining, like in Star Wars, like Luke Skywalker's house. How it just had the big
Little
dome
on Tatooine.
made of on Tatooine, made of it looked like sand, so just like making like a sand dome.
Yeah, so you need something like that, because again, like when we went to the moon, the lunar lander was, I forget, but as I recall, like paper thin, right? Like it wasn't a long duration, or they weren't planning on staying there for a long time. So on Mars, if you're going to stay there for like a year and a half, which is generally the mission architecture says about 6 months trip to Mars to get to Mars, a year and a half on the surface, 6 months back. So if you're going to spend a year and a half on the surface of Mars, you need to do something to shield yourself from radiation once you get there.
Definitely. So in the movie The Martian, there was a severe dust storm.
Yes.
From what I understand, that's wouldn't really happen, right?
Correct. So, and this is, so I got to say though, because not a knock against Andy Weir at all, because when he was at JSC a couple of years ago, he gave a presentation and said, okay, before you guys ask any questions, I know that the dust storm wasn't realistic.
He was probably very nervous about his audience. He's like, these are the guys that know. Oh, no.
So he just said, I wanted to write a book about kind of like Robinson Crusoe on Mars, and I had to do something to get him stranded there.
Right.
So the dust storm is not realistic because Mars's atmospheric pressure, again, is less than 1% of the Earth's atmospheric pressure. So even when you have very fast winds, they're not very strong. So you could have like 100-mile-an-hour gust, and it'll feel like a less than 10-mile-an-hour wind on the surface of the Earth. So it's just not strong enough to push anything over that size. The other difference is there are dust storms on Mars, and they can be planet encircling.
Right. You've
which
mentioned
is
that before.
which is really interesting. Something that obviously doesn't happen on the Earth.
Right.
Thankfully.
Yeah.
But the way that it works, and you can go look at, there's pictures of this, because the Opportunity rover has been there during, I don't think it was a planet encircling one, but at least a very regional, like large scale dust storm. And the way that it looks is at the beginning of the dust storm, you have, or before the dust storm starts, you have pretty clear skies. And then something like 20 to 30 days later, you can't even see the sun at all anymore. It just maybe gets slightly lighter or brighter during the day. But it's a very gradual increase from day to day. It's not like in The Martian, here's this massive dust storm barreling down on us. Let's all go inside.
It's tipping the MAV. It's like,
So Mars does have these really large dust storms, but they're just not strong enough to really have to worry about much.
Does it have its own weather too? It has like lightning and stuff, right?
I don't know about lightning. It might. I do know of people who have said that it probably does have lightning, and the lightning could create interesting chemicals that we see in the atmosphere and on the surface, and so maybe that's a signature of lightning. I don't know that we've ever directly observed lightning. But Mars absolutely has weather. It is still a very dynamic place. The main agent of change on Mars is wind. It just happens at a slower pace than on the Earth. But Mars has sand dunes that march across the surface. It has this dust that can blow all over the place. Mars has dust devils, so if you live in a little bit drier, more arid environment, and you know what a dust devil is, we see dust devils on Mars all the time. Yeah, they look kind of like little tornadoes. Yeah. Good. Yeah, a sand tornado is a good description, and we've actually been lucky with some of those. So Spirit and Opportunity, I know this happened with Opportunity. I'm pretty sure it happened with both of them. So they're solar-powered rovers. So they saw the output from their solar panels was decreasing over time because you're constantly getting dust settling out of the atmosphere. And then, so I can't remember the exact numbers, but it had gotten down to like half of the solar panel output from when it landed. And then they look at the data, and from one day to the next, it jumps back up to the same amount of power they were getting on like day one of landing. And so they look at their solar panels, and they've been completely cleaned. So what they think happened is a dust devil passed directly over the rover and did us a huge favor by cleaning off the solar panels. Like, there's no way that Opportunity would still be alive had that not happened multiple times.
Wow. Okay, so they're pretty frequent then. If they're,
this happens all the time. And you can actually see the dust devil tracks from space. A friend of mine, Dave Choi, did some work on this where you can see dust devil tracks all over the place because what I said earlier, you have this bright red dust that gets kind of laid down uniformly over the surface, and when a dust devil comes through, it'll suck that up off the surface and move it somewhere else. So you see these tracks of dust devils all over the place, and at first we didn't really know what we were looking at, and then somebody, I forget who, said, hey, those are dust devil tracks. And yeah, they are all over the place on Mars. We have seen them everywhere we've been looking, we have seen them.
It's just amazing that you can think of, you can imagine what's going on at the surface level of another planet, as if it's just like another place on Earth, but we're talking about
and a completely different planet.
A completely different planet. Yeah. So that is wild.
Yeah. And another thing that Phoenix saw is we actually saw snow and frost deposition. I mean, it was, teeny tiny bit of snow.
Right.
But it was snow.
Yeah,
so
it's kind of like how, like I said, I'm from Pennsylvania, and we get snow all the time. But here, when there's snow, everyone loses their minds.
Yes, it might be. Well, it might snow on Mars more frequently than in Houston, but it doesn't snow a lot.
I would like to see snow on Mars. That would be pretty cool. So, being a planetary scientist, and you've alluded to a lot, if talking boots on the ground, this is what you have to do, this is what you have to think. I'm assuming you've thought a lot about what a human mission to Mars would have to look like to be successful.
From a scientific perspective?
Yes.
So I would say probably the holy grail from a scientific perspective, and this is one of the things that humans would really enable, would be the ability to drill. Because, we say on MSO we have a drill, and that's true, but we can drill down all of 6 centimeters. So, a couple, 3 inches, 2.5 inches. So not very far. We are literally just scratching the surface of Mars.
Yeah.
And if you want to go to a place, again, getting back to the radiation environment, the radiation, you have a lot of radiation or energy deposition in the top meter of Martian soil. So any life that existed there that was maybe, billions of years old has been either heavily transformed or completely destroyed. So it would be really hard to find the signature of life anywhere within the top meter. So we need to go deeper, and if you want to go really deep, you need humans, because drilling is something that is very difficult to do kind of in an automated way, even on the Earth. You need people there to kind of troubleshoot when things go wrong and fix stuff that breaks or whatever. So that, to me, is one of the things that humans would do. The other thing is, I think we've been studying Mars from the surface, like I said, for 40 years now, but still we've only landed in, let's see, so we have Viking Lander 1 and 2, Pathfinder, MER, Phoenix, MSL, so 7 successful landings on the surface of Mars. So that's like saying pick 7 places on Earth spread out by 1,000 miles or so each, and tell me about the entire planet. And obviously that's not like the whole history of the planet over 4.5 billion years. And by the way, you can only go about 10 kilometers from wherever you land. So
Wow.
There are so many other places on Mars that we know nothing about, that you look from orbit and say, what the heck happened there?
Yeah.
What is this? What's going on there? And there's a lot of places from orbit as well where some places we can kind of tell something about the mineralogy. Other places they're completely covered in dust, so we really have no idea what the mineralogy is of what's underneath it. So another thing that humans will give you is the ability to go farther from wherever you're starting. And again, the boots on the ground, people saying, hey, this looks really interesting, let's chase this down and go over there. Also, we would be greatly benefited by bringing samples back from Mars on purpose, where we know where they come from. Like,
Right.
we have Martian meteorites, but we don't really know where they came from. So knowing the context of the samples and being able to use the instruments that we have on Earth, which are much better than the instruments that we send to Mars because of size, volume, power, whatever. We could do a lot with the sample returned from Mars, and astronauts, like from the moon, astronauts brought back hundreds of kilograms of sample. Now it's a bit more expensive to get back stuff back from Mars, so we might not have quite as many samples, but we would definitely bring back samples with the astronauts. So that's another thing that having people there on the ground enable you to do.
Yeah, knowing the science, this will be the last question, and then we'll kind of wrap up. But
Okay.
knowing the science of the planet, kind of, what are some of the key things that we have to be paying attention for to make sure that humans can survive and operate in the most efficient way? Because like you mentioned radiation a couple times. Radiation is obviously a concern, but what do we have to think about in terms of the way we move and how far we can go? And you obviously said, you already talked about a mission profile, how long we can be there.
Right. So radiation is one of the big ones. We're still not totally sure how the human body works for a long period of time in a lower gravity situation. Like, we have people in 0G, right?
Right.
But Mars is 40% the gravity of the Earth. We don't really know what the effects are of the human body. Unfortunately, that's incredibly difficult to simulate, so we probably really won't know until we go.
Right.
Otherwise, though, there are other kind of environmental hazards that you need to be aware of, like you referred to the dust. So that's something that you just need to make sure that you have good filtration systems.
Okay.
It's one of the main problems for the dust, though, is for the suits. Like, if you have a spacesuit with seals and you have joints that move, and you have dust getting into those joints, which we know it did on the moon, then that can be problematic. So, how do you design your seals? How many replacement seals do you need, or design your spacesuit to be repairable by the astronauts on Mars? But this is also kind of an open question, is that we don't really know the nature of Martian dust. We don't know if it will be kind of as sharp and damaging as some of the lunar dust, because the lunar dust and Mars dust form in two different ways. Like, we know the average particle size of the Martian dust that gets into the atmosphere is like 5 microns. So that's great. It's good to know that, but you need to know a little bit more about the size, shape, hardness, those kinds of things of the dust, about the dust when you're talking to people about seals for spacesuits and spacecraft. The other thing is being aware of potential toxic things on the surface, like perchlorate, for example, which is an oxidized chlorine molecule that the Phoenix lander discovered in 2008. And so we know that perchlorate is toxic to people, but at really high quantities. So it's less of a concern for inhalation for people, however much perchlorate might be in the dust. So as I like to tell people, as long as your astronauts are not eating kilograms of soil every day, they're fine. But
kilograms?
It really would have to be.
Soil.
Yeah, right. So that's generally fairly low on. Hey guys, don't eat dirt. Yeah, okay, we got it. We checked that one off.
It's very tempting, but
But so the one thing that we do have to do more research into is if you grow plants in soil that have perchlorate, there are some plants that can concentrate perchlorate in certain parts of the plant. So you need to know, like, okay, if we're planning on living off of this, first of all, can it grow in a soil that has perchlorate? And if it does, where does the perchlorate go? Is this something that we need to be concerned about? So those are kind of questions that we're answering. But the exciting thing is that we have the data to actually be able to address those questions, right?
Yeah.
Like, I mean, 40 years ago at the end of Apollo, when we first talked about going on to Mars, we didn't know any of this stuff.
Right.
We hardly knew anything about Mars, but now we have a significant amount of experience and a large body of knowledge about what the surface of Mars is like, what all the stuff we talked about today, what is the weather like, what's the temperature, what's the pressure, what's the chemical composition, what's the mineralogy, what are the physical properties of the soil, if you want to build something there or land something, what's it like, what are the things that we need to worry about. And that's what's really kind of amazing about the journey to Mars right now, is that really for the first time we have the information to go out and we know the questions that we need to answer. We don't know the answers to all the questions yet, but for the most part, we know a lot of the questions that we need to answer. And I'll just add one final thing, so you don't think it's all bad. There's a lot of stuff, and a lot of the work that we're doing isn't just what are the bad things about Mars, but what's on Mars that we can use for humans to help enable future exploration. Like there's an instrument called MOXIE, and sorry, that's an acronym that I don't know what it stands for, but basically it ingests atmosphere and it breaks the carbon dioxide and oxygen, so you're forming oxygen, which the idea is you'd use that for your oxidizer in rocket fuel.
Nice.
And you can also, one of the things that I'm directly involved in is trying to extract water out of Martian materials. So water can be really useful because astronauts need water to drink, for food. You can break the water through electrolysis or other ways into hydrogen and oxygen. You can breathe the oxygen. Hydrogen and oxygen can be used as rocket fuels or fuel for a fuel cell. There's all kinds of stuff that you can do just with water. And so every kilogram of material that we don't have to bring with us makes it more likely that we will actually be able to go, because it lowers the cost and complexity of the overall mission. So we're trying to figure out from what is on Mars today that we can use to our advantage. And again, these are questions that we're now being able to answer based on the exploration work that we've done over the past 40 years.
I'm excited. I want to go to Mars right now.
Me too. Let's do it.
That was a nice little summary of all the things we talked about too. That was great. Well, I think that's all the time we have. Doug, thanks for coming on the show today.
My pleasure.
That was awesome. So cool. I learned so much about Mars. I had so many questions, and almost all of them got answered. For the listeners, if you do want to know more, I'd be surprised, but actually there are way more questions. We can talk forever about Mars. But if you want to stay tuned after the music that we have at the end here, we'll talk to all the sites you can go to and learn more, and maybe you'll find a question that you want to ask, and we'll tell you how to submit that. So thanks again, Doug, for coming on the show. We'll see you maybe next time, maybe one more time. Who
Sure.
knows?
Stop of the space shuttle.
Roger, 0J, and I feel fine.
Shuttle has cleared the
Became
tower.
a stage for all mankind.
Actually, a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston, welcome to space.
Hey, thanks for sticking around. So today we talked about Mars, the red planet, and everything about it. But when I say everything, I don't truly mean everything. Obviously, there's a lot more. We may do another podcast in the future, but if you want to know more about the red planet right now, just go to nasa.gov. Right at the top, there's a little gray bar, and you can see the Journey to Mars. That's one of our campaigns, and if you click on that tab, you can learn all the new things, all the new features and all the new articles, scientific findings, right on that page. So just click on the Journey to Mars page to go there. On social media, we're pretty active. Doug Archer here, Dr. Doug Archer, is part of the Astromaterials group, what we call Aries. You can find them on Facebook and Twitter and Instagram. And you can also go to the NASA Johnson pages, Facebook, NASA Johnson Space Center. We're also on Twitter and Instagram. On any of those pages, just use the hashtag AskNASA on your favorite platform, whichever one you like, and submit an idea for the show. Maybe you have a question about Mars, or maybe you have a new idea or a new question that maybe we can make a whole podcast episode out of. So make sure to mention it's for Houston. We have a podcast, and we know to bring it on this particular show. This podcast was recorded on April 20th, 2017. Thanks to John Stoll and Alex Perryman for producing the episode, and thanks again to Dr. Doug Archer for coming on the show. See you in 6.79 sols. It's a week in Mars. You know what? Never mind. We'll just see you next week.